Our next question is all about data types. This question is, what other data types do I have in SQL that I can work with? Because I know in a proper programming language I have integers and strings, I have lists and sets and frozen sets and tuples if I'm in Python. What do I have in a language like Postgres? Well, in Postgres and in many of the other tools you might use, you might see that you can define something as a string. If you use SQLite, SQLite is quite limited in the data types that it has. And so if you wanted to represent a date, you'd represent a date as a string. You'd have operations that interpret that date as a date. That's very similar to how you think about Shell. Shell doesn't really have any data types except strings. You can interpret a string as a numeric value, but you can't really store a numeric value in Shell. Well, in some database products like SQLite, you can't really store a date value. You can store a string, which then you have functions which operate on as though it's a date. Whereas in Postgres, you actually have real data types. You have a very rich set of built-in types. From the perspective of some of the numeric types, you can see here I can use pg_typeof to determine the type. So I have an integer, I have a numeric value, and I have this unknown. And the reason why I have this unknown is it is very common within Postgres for anything that's not a numeric type to be encoded in a statement as a string, which is then parsed into the type that you want. And so my interpretation for why Postgres says I don't know what this is, as opposed to saying, oh, this is a textual value, is, you could force this to be a textual value, is what Postgres is thinking is, oh, you just encoded it this way, you just wrote it out this way, but later what you want to do is you want to turn it into a date. And so I'm not quite sure what you're referring to. Postgres does a lot of work behind the scenes to try to figure out how to do implicit conversions. So if you say, oh, select this string into a tables column, and that column happens to like an insert statement or a select into, and that column happens to be a datetime type, Postgres will implicitly perform that coercion, will implicitly convert that to a date value. Now, here you can see, some actual data that I've created. Here I have one row that I put into this table that has a textual and a date column. I can select from this, and you can see that when I select from this, that insert statement didn't insert a textual type here. It actually inserted a date type. There was an implicit coercion here. I can force a coercion. I can force a casting. There's two syntaxes for this. This is the more general SQL syntax, and this is a more specific Postgres syntax for saying, give me this value as a date. And you see this all over the place in SQL queries in Postgres. You'll have a string that encodes the data, and then you'll say immediately after, oh, but I don't mean this to be a string. I mean this to be a date. I mean this to be a time zone. So let's take a look at some of the things that we can do. Here, you can see I can cast this thing as a date in these two ways, and it's actually casting as a date. But one important thing that I want to share with you beyond the implicit coercions that happen is sometimes with the numeric tower, there are other types of implicit coercions. Here I have some random values that I'm selecting with a select from value statement. And if the value is greater than 0.5, I turn it into an integer. If the value is not greater than 0.5, I keep it as a real. And you can see, oh, that's a real value. So it's a real number value and then two integer values. And you might be curious what the type of this expression is, and you'll see it's real every time. One of the things is the types do matter in Postgres because Postgres is strongly typed. A column has one type, and it can only have one type. And so if I tried to do something really weird here, like I tried to make this a text together with a real number, Postgres says that's not possible. There's an implicit coercion where it's taking that integer value, it's still truncating it, creating an integer value, but then it's lifting it up the numeric tower to the closest compatible type, which happens to be this real type. Note that this is a real type, not a sized floating point type. There are sized floating point types in Postgres, and there are sized integer types as well. There's an int2, an int4, and an int8, but usually what we're referring to is some numeric value. There's also a real and a double precision. You can see that's a float 4 and a float 8, a 4 and an 8. But usually what we probably want is some notion of a decimal or numeric type, not specifically the bit width. Because we can think that if we have the bit width, then we worry about things like overflow and underflow, and that's maybe a little bit too much for us to worry about. But because SQL fundamentally has as part of its consideration how the data sits on disk, the sizing is going to be important. In a very similar way to in pure Python, we see that integers do not have a bit width, but in NumPy, they do have a bit width because NumPy is talking about contiguous data with a uniform striding. Well, in a very similar sense, SQL is talking about data that's laid out in disk in order for you to be able to access it very quickly. And so the fixed sizing of that is generally important. Now, one thing I don't want to talk about too much is the text sizes. Historically, there was a distinction between variable characters and fixed characters. Oh, this is 8 characters. And that allows you to quickly scan, oh, what's the next, what's the next, what's the next? Because you just jump by 8 bytes. And then people introduced variable characters, things which could be larger or smaller, because you could say, well, if sometimes it's 1 character and sometimes it's 8 characters, I'm wasting space in a lot of these situations. And you could think that in order to find each value, you have to know what the length is. This is actually not too dissimilar from what tools like Arrow give you the ability to do, which is store a variable length string without any additional padding, but finding ways to still preserve fast lookup of those. I don't want to go into that too much because some of our intuition around whether we should use variable characters or characters is a historical intuition. My understanding is, for the most part, when I use Postgres, I just specify broadly if I'm working with either integer values, or decimal values, numeric values, or textual values, and I let the underlying database engine figure it out for there. If I really need to come back and adjust the total amount of space that's being used, then I address that secondary. So I don't really sweat all of the details at this level. Now, one thing that I might sweat a detail of is I might want to fix the precision and the scale for my numbers. I might want to say this number, numeric value, only has a fixed amount of precision. It only has two digits after the decimal point. And one thing that you might be misled in thinking is that even though they call this arbitrary precision decimal values, it's arbitrary in the sense that you can pick it, not in the sense that it has infinite precision. One of the things that you know from your use of pure Python is, as a consequence of any finite modeling of a real valued term, there's going to be imprecision and inexactness, and this leads to weird things like 0.1 plus 0.2 not equaling to 0.3. Or it leads to weird things like commutativity and associativity not holding because you have the saturating behavior when you lose the ability to exactly represent numbers. For example, in a 64-bit IEEE 754 double precision floating point type, 2 to the 53 plus 1 cannot be exactly represented. And so we have this really weird behavior that if this is our x value, well, x happens to be equal to itself plus 1. And you might say, oh, well, maybe my database, maybe Postgres saves me from this. It cannot. These are fundamental limitations of a non-symbolic finite memory encoding of these data types. And even though you have things like the textual type in Postgres, and even though you have things like these numeric types, you're still working with finite memory. And with the numeric type, you're still working with finite constant amounts of memory. And so just like the decimal type might be able to solve the 0.1 plus 0.2 equals 0.3 problem, but might not be able to solve other types of problem, like, for example, what is not exactly representable in decimal, like 0.3. So let's see, does this equal to 1 exactly, or does this equal to 0.9? Oh, no. Sorry, 0.3 times 3, equals 0.9. Or if I do, well, actually, that should definitely not equal. If I do this times 3, let's see if it goes back to 1. And you can see 1/3 times 3 doesn't equal 1. Well, that's because the exactness of being able to represent this in decimal. Well, you can't represent 1/3 in finite memory exactly. And Postgres doesn't really help you. And if you think about this more generally, things like pi or e, these transcendental numbers, the number of digits after decimal place is infinite. There's no way in finite memory to store the exactness of this. And so when you're working with things like, the numeric type, you can set the number of digits of precision you have, but you're still going to have to worry about things like inexactness and imprecision. You're still going to have to worry about things like these values not necessarily being commutative or associative when you add them up. And you're still going to have to worry about things like 0.1 plus 0.2 doesn't equal 0.3. It's just the case that whatever base you have is going to determine what is not precisely representable. One thing that Postgres has that you'd think you might want to use, but I very rarely used, is the money type, which is basically a data type with the smallest tradable denomination, the non-decimalized smallest tradable denomination of that value, like cents for US dollars, as a fixed size for the number of digits after the decimal point. So this isn't a store billions of fractions so that if we do lots of mathematics on your bank account, we don't find 1 cent missing here, 1 cent missing there. No, this is just a money type that puts a dollar sign when you print it out at the beginning and stores however many digits are relevant for that particular locale for that particular type of money. So it sounds interesting, but I don't really use that much. One thing I do use a lot of is the date time and timestamp types. Here you can see I have a timestamp. And I have two timestamps. One where I can control the number of digits after the decimal point when I'm storing the number of seconds. So here I have 9 o'clock and microseconds, and here I have 9 o'clock and milliseconds fidelity data. When I store timestamps, I can store them with or without a time zone associated with them, depending on whether I'm working with time zone aware or time zone naive data. And I do have distinct types for just the time of day and just the date, separate from the combined date and time type. I can perform time delta-like operations. I can subtract timestamps and get a delta value, and this is what Postgres calls an interval value. And I can customize, or I can ask that interval type to store only a portion of the interval rather than doing like a dot total seconds divided by whatever, like I have to do in Python. Here I can say, oh, give me intervals of days, or give me intervals of seconds. Maybe I think it's like sec here. Yeah, give me intervals up to seconds, or give me intervals up to the minute. So it's a little bit easier to work with. I also have enumerated categorical types in Postgres. And so here I can represent a value that's fixed to 3 possible values, red, green, or blue. And like your pandas categorical, by default, these are ordered. And so here I can say is red less than green. Whether that's meaningful or not is secondary. Pandas gives you this ability to say whether it's ordered or not. You have a flag here. In Postgres, it's assumed to be ordered. And so that might be useful or not. One thing that you could do with this, however, is you could look up ranges from a lower bound up to and including an upper bound. So you could say, give me all the values in this enumerated value from yellow to blue. And where this is useful is, and it's the same place where enum.enum is useful in pure Python is, you could create expressions which operate on the full range of potential values. And so what if I had some table and I had some counts, or I had some entries of red 1, yellow 1, orange 1, green 1, and I wanted to do a group by. And with that group by, I wanted to sum up how many I saw, but I wanted one entry per possibility, even if the possibility didn't exist in the table. Well, this is a case where I could unnest my enum, and through some sort of join, I could say, oh, join against all of the possibilities. And so this is where this enum type is actually very useful. It gives you the ability to access what all the possibilities are. You've seen me do this before. I can create compound types in Postgres. Here I have a compound type, a row value that has 2 independent entries. And if I look at the PG type of this, you can see something kind of interesting. Its type is record. So it's a record of some sort representing some composite value with 2 individual components to it, namely an integer and a string. And I can create a record type that I can pass around. So I can create structure types like name tuple types or object-like types with fixed fields that I can pass around as single values. And I can even create arrays of them. Postgres has the ability to represent multidimensional arrays. And note, these are proper multidimensional arrays. They are not nested arrays. You know this because each array dimension has to be uniform. So this is like a NumPy and D array, not like a list of lists. Well, I can have nested arrays or just arrays of my record types. So here you have the most direct equivalent of a list of tuples in Postgres. Here, our tuple is our record type that we defined, and we have an array of these. I can also express range values in Postgres. So here is something similar to my interval type in Pandas, a range from 0 up to 10, not including 10. And I can express each one of these with a more fine-grained expression, or I can be more deliberate about whether I include or not include the endpoint or the beginning point, what kind of interval notation I'm using. And so here you can see a very common use case. I have a string to represent an interval, and then I immediately cast this into the desired type. If I have a range, I can query that range for what its upper bound and its lower bound is, and I can store these like any other value in an array. So this is an array of 3 ranges. Now, the interesting thing is there is also a multi-range, and this is distinct from a multi-range. This is 3 independent ranges that don't necessarily have a relationship to each other. This is 3 ranges that are related to each other in the sense that if the ranges are overlapping, they will elide the contained most element. And if they are non-overlapping, you can see what it's done. Kind of interesting, huh? It's given you the overlapping set. And if I have a discontinuous portion for this range, so let's get a discontinuous portion of the range. Let's see what it does. The multi-range gives you the ability to have seamless collections of discontinuous portions of a range, and it smartly knows how to join these up. And I really wish Panda's interval index could do this. This is the thing that's missing from the interval index, and it's right here in Postgres, and it's so useful. The last type I want to talk about is the JSON type, because it's very likely that we're working with data that was originally stored in some sort of document structure in JSON, and so Postgres has the ability to store string data. Well, actually, I take this back. Postgres has the ability to store raw JSON input data. It just stores it as a string. And it has the ability to interpret string data as though it were JSON data. And so this coercion to this JSON type, the real value of it is not that I'm storing it differently. The real value of it is that I'm asserting that it's got to be valid JSON. And if I create some invalid structure here, some syntax error here, I get a warning for that. The JSON type is still storing this as a string. And so in the underlying storage of this data, you can see if there is extra white space or formatting, that's being preserved exactly. Generally, what I probably want is not the JSON type if I'm storing this long term and I don't need the exact user input. I want the JSON-B, a binary encoding of this JSON data that is actually stored distinct from the text. It's going to be a little bit slower on insert because I have to convert it to this JSON-B type, but it's going to be much faster on retrieval because it's now a binary encoding of the underlying JSON data. And it allows me to perform certain operations like asking, is this JSON array a subset of this other JSON array? And I can do that with the array type as well, but I can start performing some very complex computations on this stored JSON data. I can do that very quickly. One of the things you can see is I have the ability to perform like joining operations. I can join 2 strings. I can join 2 JSON arrays, and you can see that it actually concatenated the arrays. And I can take some stored JSON data and I can use JSON path queries, very similar to your jQuery CSS selector style, to select out data. This may be why I want to store this as JSON-B data so that I can then perform intelligent JSON level operations on this, filtering it, transforming it, creating new structures, and performing path expressions. And so here's what we looked at. We looked at the numeric types and how to model them, different datetime types, the interval types, array composite types, and JSON types, and we saw that very much like our common programming languages, at least the ones that are very set on this notion of typing, our database is very similar. The exact types that it has are largely overlapping to the types that we've seen before, and it's more like, we would say, a NumPy or a Pandas situation where we care about how much memory is being used and what the disk layout of this data is, as opposed to, oh, we have this arbitrary sized integer that grows as the value grows.